All right. Sorry for the wait, folks. So just to start, so what we're going to be talking about today is network intrusion with deep learning. So the main ideas I'll be going over are basically the big data infrastructure behind solving that kind of problem. Yeah, sorry, not Japanese. So if you want, you may need a receiver if you don't already have one. Maybe go get one now. So I will try my best to speak slowly, but what I am talking about is going to be a slightly complicated topic since it will involve AI, artificial intelligence. Okay, so starting off, I'm Adam, the co-founder and CTO of SkyMind. We're an AI company based in 6 time zones. Co-founded in San Francisco. I actually live here in Tokyo. So I think we're one of the only AI companies from Silicon Valley that actually has an office here. Or if they're rare either way. Anyways, so we build solutions like detecting hackers from raw packets. So like raw internet traffic. We do large-scale pattern recognition. We don't typically do deep learning for the typical applications you see out of Google and Facebook. We solve problems for banks, telecom, and the traditional enterprise, hence the name here. So next. So what I'm going to go over today is kind of the task of network intrusion, anomaly detection in general. So what is anomaly detection? Like what are other examples of the problem of anomaly detection? An alternative case study in anomaly detection, so a real example of a problem we have solved for customers. Why deep learning for this? Because you typically hear about deep learning and it's very hard. Normal mortals can't do deep learning. You actually can. And you can apply it to real problems that your company actually has today, which is what I want to prove here. And I'll introduce it in the context of network intrusion, where you normally apply statistical techniques rather than machine learning. And then I'll show you why deep learning is actually very good for this kind of analytics. And then what I'm going to do is I'm actually going to walk through, with pictures, a real scenario of a production deployment of a network intrusion system that would use deep learning in real time. So you'll see all your good Scala stuff like Spark, Kafka, the JVM. So there's very much a lot of JVM-oriented things. So things you've seen before. So it's not all going to be just AI and math. And then finally, I'll actually have a demo, just a little mini one, just so you can see what an application of network intrusion with AI looks like. Next. So network intrusion. So what is network intrusion? It's detecting the hackers. It's finding illegal traffic or traffic you don't want in your network. So when you think of network intrusion, you might think of the movies, The Matrix, where everybody's like, it's hacker versus hacker. In practice, I'm just going to warn you now, most network intrusion is actually internal. You guys are the problem. Humans are the problem. Clicking on a link sent by a random person, and then opening that link, and then downloading that file onto your computer. That's actually the typical network intrusion that happens in the real world. What I'm going to talk about today is just a simpler scenario where you're trying to define basically illegitimate traffic like SSH and other kinds of things, like traffic that connects to your network and attempts to break in. And so that's going to be based on raw, what are called weblogs, so click traffic. So it's not quite a real network intrusion system would be a lot more complex. So the goal is to show you what a streaming application with deep learning could look like. And in this case, network intrusion is something everybody, I think, kind of understands. So let me see, I think I got. Yeah. Okay. And then yeah, I guess mentioning one other thing here. So when I say weblogs, just for context, I mean when you go on the internet, you click a link, and then you get a web page back. When you got a web page back, the person or the server sending the web page logged your traffic. They logged your IP, they logged your browser, they watch you basically. Like they want to know who's asking for their web pages. And so what I try to do here is I focus on data mining that kind of traffic, your Apache logs, things you would put into your Elasticsearch. Elasticsearch is a search engine database. That's where a lot of people typically store logs. So this kind of traffic is stored in these search engines. So what I want to show you how to do is mine that traffic for bad actors. Next. So anomaly detection it's an interesting problem. It's a problem people have had for a very long time across various industries. One of the typical ones you might think of is banking. You get a call from your bank saying, was this transaction real? You've probably seen that somewhere. And so some person at a bank got a flag from their system saying, this is bad behavior. You probably didn't spend this money yourself. This is fake. So that's an anomaly because you have normal behavior where you're buying lunch. Maybe you bought something from Amazon and it's you doing it, right? So that's normal traffic or normal spending. Whereas the anomaly is somebody else who's not supposed to be spending your money spent it somehow. And so the goal of anomaly detection is, I guess, another way to say this, I'm not sure how to say this in Japanese, but in English we say finding the needle in the haystack. So it's a great analogy because what you're trying to do is you're trying to look for rare and targeted patterns in data. You see. All right, keep going. Next. Okay, so one use case that we've actually solved for customers was for the biggest telco in France Orange. So we helped them tackle a multi-billion-dollar problem. In France and Africa, they actually have telco infrastructure. So they have users there. It turns out there's a lot of French-speaking people in France. Anyways, or in Africa. And so one of the things people do in Africa is they actually steal traffic and leech off of the servers or of the telco infrastructure in France and Africa. So they put something called a SIM box in Africa, and they basically send calls from Wi-Fi through those SIM cards onto the telco network. And so the goal with this problem is to find that traffic and shut it down. So what we actually do is based on what are called call detail records, like this person called this person at this time. Like when you scroll through your phone and you hit call and then you have your recent calls, that's a call detail record. So we actually look through billions of those transactions, billions of those records, and we're able to find traffic that was stealing from the telco. So this cost them billions of dollars a year. And what we did was we actually used an unsupervised, so no labeled data, unsupervised. That means no labeled data for finding anomalies. So we applied deep learning to call detail records. Basically, we built a vector representation of the call detail record that the neural and basically because of that vector representation, we were able to automatically find patterns. Because if you think about groups, if you think about grouping these records, you have normal traffic and you have abnormal traffic. The vector representation was able to clearly separate the normal traffic from the fraudulent. And so it turns out we can do something similar with network intrusion. So next slide. And so the whole point of deep learning for this is, just give you a brief history. So deep learning is typically funded to the tunes of billions of dollars by large ag tech companies such as Google and Facebook. And more recently, anyone who has a recommendation engine, such as Amazon and Netflix, everybody does some sort of large-scale deep learning to basically recommend, like, to basically say these two things are similar, right? Like, so anytime you have behavior and you want to find similar patterns, then you would use deep learning for this. So this would be for targeted advertising. The person who clicked on this link is also maybe likely to click on this link. The person who watched this movie may also like this movie. It turns out that deep learning is very good at building a representation that makes it that allows the computer to separate more cleanly these fine-grained attributes of your activity. So if you think about activity, it's you watching a movie. It's you buying some sort of an item on Amazon. It's you hacking into a network. It's you spending money. So all the thing these things all have in common is a timestamp. So it's a behavior over time. So it turns out deep learning is good at any application where you have some sort of behavior over time that you want to surface. Right? Like, so it's good at finding hidden similarities in data automatically. Deep learning, so sorry, I apologize to the translators here. There's one word I'll use called representation learning. Representation learning is, in short, is basically it's the neural net that automatically, it learns its own patterns. It learns its own representation of the data. And it uses that representation to classify and cluster input data. So an input data in this case could be your call detail record, you buying an item on Amazon. Those are all inputs into a neural network. And then usually the person using the deep learning model has some sort of a target behavior they're looking for. What are they likely to buy? How likely are they to buy it? How likely are they to buy the item again? How likely is the demand for this item going to increase? They want to find targeted patterns like that. So deep learning is good at classifying and clustering data, raw data, and often from multiple domains. So click traffic from your mobile and your desktop. So click traffic is like you visiting websites and using both your mobile and your desktop behavior in one place. One model can use both representations to then target you with ads. So that's typically where deep learning has paid off. But a lot of what we've seen in the market is that deep learning is also very good at things like fraud detection or network intrusion. And so what we tend to tell customers, despite the lack of research and development and papers in this field on these kinds of use cases, we point to how the structure of the problem is set up. You have a target behavior you want to find. And in this case, the one behavior in advertising is clicking. And then in hacking or anomaly detection, in this case, it's just transactions or actually, let me rephrase this. You have web traffic where you want to find whether the person is likely to buy an item. You also have web traffic for finding hackers. Those are both same kind of data, but different target patterns. So it turns out deep learning can be used for both kinds of pattern recognition. But what we typically think of deep learning for is media. So you typically hear about computer vision, image recognition. You hear about speech recognition, speech to text, machine translation, taking English and translating it into Japanese. Turns out it's still not very good yet, don't worry. So you typically see deep learning for those kinds of applications. So that's actually why I wanted to cover just a simple time series problem today. So you could maybe think about deep learning for your company on normal data, problems people actually have. Okay, next. So what I want to do is I want to go through just an example scenario where we visualize what a potential production cluster could look like for detecting hackers in real time. So this is where it's going to use all the stuff that you guys love: Scala, Akka, Play, microservices. All these things that you've probably seen throughout this conference. So most of this talk is going to be on how to build a system like that And then I'm going to keep it kind of light on the math in the deep learning part, but I'm happy to answer any and all questions you may have on that. Next. So what we're going to do is we're going to start with thinking about the data. You know, a deep learning, a neural network cannot learn anything without data. So any data science problem that you may have needs some sort of input data. There has to be a data source of some kind. You know, you might see this from a relational database such as MySQL, Postgres, Mongo. Please don't use Mongo. You know, any NoSQL database, right? You know, anyways, you have some sort of a storage mechanism, and you have a data source. This is your input data. This is what the neural network will learn patterns from. So any and all machine learning or deep learning needs the input data. And what we're gonna actually cover is how you convert this raw data from your database to a representation that the neural network can then use for network intrusion detection. Next. And so let's walk through an example scenario. So typically you're using Kafka or MapRStreams, stream sets. You have some sort of streaming software. So a stream, what it does is it takes things from raw web logs, such as your Nginx or your Play server or anything that's a web server. It takes that raw traffic and then it puts it onto a worker queue, a stream. So Akka streams is maybe what you might think of here, if all of you know Akka, or Kafka. You know what it does is it takes things from raw data, it puts it onto a queue. And then something else consumes from that queue. So you use PubSub to send the data somewhere. So you're routing the data in real time to something to somewhere where you can then go analyze it, right? Like so, the goal of this is to take raw data, raw unstructured data, and then route it to various places in your infrastructure where you may want to analyze the data for different reasons. So, for example, you know connecting to a streaming framework of some kind, you may want to send the data to your targeted advertising and your network intrusion. So you may want to detect hackers, and you may want to detect user activity to understand what users are doing on your website. So that's a pretty typical scenario. You have one data source, and you have multiple use cases. So this is for companies with a large-scale infrastructure. So you're using streaming to take the data and then send it places. So that's this idea of a data spout. So think of a spout as like it's a source. Okay, next. And so you take the data from some sort of a streaming place, such as Kafka or what have you, and then you land it into something called a data lake. So a data lake it's kind of a big data buzzword, but in short, you can think of it as HDFS, Hadoop File System. It's a place where raw terabytes of data just gets dumped and archived for analysis. And then what happens is data engineers then access your data lake, your central data store, and then they clean the data in some way and then prepare it for data scientists who then analyze the data. Next. And so when I mean by pre-processing, so it turns out raw data is actually very hard to deal with. So what I mean by raw data, you just have these lines. You just have these lines where you log the date, you log the browser, and all these other kinds of behavior, right? But I can't use that. Like a neural network cannot use that for any sort of analysis. I can't really recognize patterns in that without first cleaning up the data. So think of it, for example, you might have a wrong user agent from a browser. That's pretty typical. You have a wrong user agent from a browser, or you have somebody faking their user agent. And then you need to find those kinds of trends, and you need to normalize them in some way. So this is something data engineers typically do. So they're taking data from this big archive, this data lake, and they're cleaning it up for data mining, essentially. Next. And so And so when you think about pre-processing, you're normalizing the data for multiple use cases. You're standardizing the data into some sort of format. So for example, if you have your web browser, right? You might have various attributes of the web browser, and you're going to have it in a standard order of some kind, right? So that standard order is then what your downstream. That's what your code assumes. Your code for your data pipelines assumes the data is in some sort of a uniform format, and that allows cross-team collaboration. And then in our case, one thing we might be doing for machine learning is translating it to some sort of a binary format. So when you're doing machine learning, you need some sort of a vector, which I'll cover in just a minute here. And that vector is typically saved in a binary format. So what have we done so far? We have a raw data. We take from the raw data. We have a data spout, a streaming thing that takes data from one place and routes it to where it needs to be analyzed, which is in a data lake. We then normalize the data, and then from that normalized data, we then use it for analysis. Next. And so from there, from taking that standardized data, we take it and transform it into something called a vector. So this process is called vectorization. So vectorization is where we're taking raw data, possibly from multiple sources, and we're transforming it into some sort of a vector. So this is very common in machine learning. Some people might call this feature engineering. So that's when you're doing data augmentation. That's when you're saying this category represents 3 columns. These are you have 3 categories. You have Internet Explorer, you have Firefox, and you have Google Chrome. Those are 3 web browsers, and then you translate that categorical data into what's called a one-hot representation. So that one-hot representation is where you have 3 columns in a vector. A vector is a list of numbers, and you have 3 columns in there that represent the web browser. And when you have so let's say you have Internet Explorer, Chrome, and Firefox, and you have a user that visited with Firefox. You would have a one-hot representation of 0, 0, 1. So 0 means that category did not occur. So that is how that neural net then can use it use it as a flag. So it can use it as a Boolean, it's a flag for saying oh, Firefox, the hackers typically visit from Firefox. That's a pattern that's a pattern you can actually learn automatically. So if you have enough input data and you transform the data in the right way, the neural network will learn to associate Firefox with hackers. So that's just one small example. So your goal with vectorization is to come up with as many observations about your data as possible, translating it into a vector format, and then putting it into some sort of a machine learning algorithm that you then tell, this is the pattern I want you to learn. So in our case, what we're doing here is we have raw web traffic. From that raw web traffic, we then translate it into a vector and then say, find the hackers based on this input data. So one thing that may not be obvious for most people is that you're going to spend about 80% of your time doing this. So if you're afraid of doing machine learning, right? Like I know some of you may be software engineers, you're not sure how to step into the field. Data engineering may be the way to do that. And what you'll end up doing is you'll end up spending time learning how to convert raw data to vectors. This is what data scientists are very good at. They're good at coming up with observations about the data for an algorithm to then learn from. So it's the data engineer's job to operate this infrastructure, including setting up connecting to the raw data source, centralizing the data in a data lake, and then outputting this vector representation. And then this is when you hand it off to the data scientist. So one thing that people don't realize when people are happy in Python land is that 80% of the work actually happens on the JVM in Scala. Scala, and there's quite a bit of, to be fair, there's quite a bit of Java out there as well. But a lot of that code is written in Scala. So most of this is applicable to you guys. If you didn't think it was, it actually very much is. And so anyways, so you get this vector representation, and then you start doing pattern recognition. Next. And so finally, we get to kind of the machine learning part. So that's when we build a model. So that's called training. So what you do is you have a vector representation of your data, your time series in this case, and you now use a neural network to train on that model. So in this case, you're training the neural network to recognize hackers from your raw input data. And so I can talk about a few different architectures. Unfortunately, the math would be a rabbit hole for a lot of people. But I'm happy to. I'm just going to name a few things you can look up. One of these for neural network models is called an LSTM, a long short-term memory neural network. When we do supervised learning, we use recurrent neural networks, or LSTMs, for recognizing patterns from labeled data in time series. So a recurrent neural network can actually process three-dimensional data. So what I mean by three-dimensional data is you have a time series length, you have attributes, and you have a batch size. So that batch size is how much do I want to learn from at once? The time series length is 5 minutes, 10 minutes, and the number of attributes is web browser, IP, like location, like those are all observations about the data. And then the LSTM can actually factor in patterns that a normal neural network can't, such as the amount of time something takes, how long something is, the duration. So a duration is just anything, it's a timestamp, right? Like so there's 5 minutes, 10 minutes, 15 minutes, right? Like so an LSTM can learn from that explicitly. And so that's what you should be using if you're doing any sort of representation learning over time series. So I'll give you an example. Google uses LSTMs for their Google Translate. I know in Japanese it's not very good, but in other languages it's fairly good. It's fairly robust. Considering the alternative to deep learning here is hiring a lot of specialists, very expensive specialists, and trying to come up with their own observations, their own kinds of data. The great thing about deep learning here is the ability to take what is essentially raw data and learn hidden patterns from it automatically, rather than worrying about doing all that extra feature engineering. Okay. Anyways, and then another model that you may use is it's called a variational autoencoder. So a variational encoder or VAE is an algorithm that learns from completely unlabeled data. So what it does is it runs a process called representation learning. What it does is it learns its own representation of the data, its own vector format. And then so what it does is it runs backpropagation or gradient descent on reconstruction error. So what the neural net does is it looks at it tries to reconstruct the original input. So it says, I'm going to take the input and my version of it, and I'm going to compare them. It's almost like a doodle. You're comparing like two. You want to see how well you were able to draw another artist's picture, and then it says, oh, that's pixelated over here, or that's bad, right? And then I'm gonna fix it, right? So it turns out that the autoencoder can actually do that with raw data. And so when we use variational autoencoders, what we actually do is we actually track reconstruction error over time. So reconstruction error is the amount of errors it made from looking at the original data and comparing it to its reconstructed version. So you track that difference over time, and it turns out that's how you can do anomaly detection. So it's actually you're basically applying a statistical technique, moving averages with deep learning. So you're using a statistical technique with deep learning to find these anomalies, and it turns out you can do this automatically. Okay, so now what you're doing is you're using one of those two models, and you're tuning. So this is where it gets tricky. This is where your intro to deep learning class comes in. So your intro to deep learning class is going to teach you the terminology needed to train one of these neural networks. It's going to teach you what gradient descent is. It's going to teach you learning rate, momentum, updaters, learning rate decay. It's going to teach you all those terms. You need a whole glossary to just even understand what a neural net configuration looks like. That's why I'm trying to avoid covering it today. But you train a model. So anyways, you train a model. Then you're doing inference. So one of the great things about deep learning in production is you can then just stream data into it. So if you set your data pipeline up properly, neural networks are actually very fast for doing inference or scoring. So you send just raw data to it, and it says this is a hacker. Like that process of using the model is actually very fast. Training, however, is computationally intensive, and that's where things like GPUs and other kinds of chips come in. Anyways, so you then take you then take the scores or however you're using the model, and then you run some sort of data visualization. So you visualize the outcomes, and that's how end users communicate with the model. That's how they use the neural net. Next. Yep. So finishing up here, actually, yeah. All right. So I'm just gonna go straight to my demo so we can have a couple minutes for questions, if you don't mind. Okay. So I have a quick demo for you guys. It's just on a website here, and I'll just show you what an app looks like. Let me see here. Oh, sorry. I'll take actually while I'm doing this, I'll actually start taking questions now. If you have any, I'll turn on my. Where did I put? My listener?
Okay, I have two questions.
All right.
The first one is, why do you need to do data cleaning? Can the deep learning learn the clean representation?
Not necessarily. So the data cleaning, typically means taking raw data, like ABC, and then converting it automatically to that one-hot representation I mentioned. So that's actually a very hard. That's actually something a human needs to do in practice. So neural networks always need some sort of a raw representation to start from, and so that's the job of a human.
Okay, but could the Nginx log could be raw enough to learn from it?
So neural nets are not magic, right? Like, so they can learn hidden patterns, but they can't learn pattern. They can't learn what one hot is. They can't learn how to take characters and turn them into numbers. That's not what they're good at. Like, neural networks themselves are actually very dumb.
Okay. And then the second question is, how do you update your model in real time? Is it possible to do it, or you are still like stuck with the training then inference?
So you can actually, the great thing is neural networks have this concept of mini batch learning, and it turns out with mini batch learning you can actually do streaming. Okay. Thanks.
Okay.
And so basically the way you do that is neural networks themselves are typically they typically learn from batches anyways. So what you do is you feed in bits of data at a time for efficiency purposes. So it turns out that can happen in a streaming context as well. So neural networks are actually very capable of doing online learning. Like, the math allows for that. And so what you would do is you would basically hook up a neural net to something like Kafka or a streaming thing or some sort of streaming software. And then what you'd actually have to do is you'd have to use microservices to actually replicate your model across a cluster to update to various users and what have you. But it's very possible. We do it. We actually do it. And so we do it with microservices. Actually, with Play. OK, so briefly, this is an example data visualization of, so these are intruders. So these blue ones are where hacking is occurring. And you'll see on the bottom right here, you'll see the input time, you'll see the time the attack happened, the attacker, their IP and location, the target, their IP and location, and then the probability that's a hacker. Right? Like, so the neural network comes up with that probability. So in real time, you're actually able to see, you're actually able to take the, data like where the attack happened, how many times it happened, those kinds of things, and then come up with a probability that the attack occurred. And then what you were doing with the neural network is you then take those probabilities and you rank them. It's a probability of the attack occurring. And so the higher the severity, the higher the likelihood the attack happened, that's what you prioritize. That's what you look into first. So you can use a neural network to actually prioritize what you look into in your network. OK. So if you have any questions about the demo, feel free. If not, I'll take other questions as well. It's time? OK. So I guess I'll be in the back there if you have anything else. Thank you.